is Carneiro, who has worked in a lot of areas and is now actually doing x86 verification from scratch.
All right. Yeah, so basically the way I started here is, the question is, can we write a software verification tool that is good enough to prove that it is correct, okay? So, you know, if you hear this and you're like me, or like Gödel, you'll think, oh, there's probably an asterisk to put on there. I won't talk about the asterisk. But what is this about from scratch? So you can debate whether this is rule number 1, but basically you probably shouldn't ever try to formalize something that wasn't intended to be formalized. And the reason for this is that it sort of forces you into a lot of necessary bad design decisions. Sort of the people who designed the original object were not thinking about formalization. They wrote it in a certain way, which made sense for their use case. And now you're trying to formalize this, and it makes things much harder. So while it can be done, you should go in knowing that you're going to have a bad day. So here's some examples of things that were not designed to be formalized. You know, the things on the left are a bunch of programming languages. The things on the right are a bunch of theorem provers. And when I say that they weren't designed to be formalized, what I mean is that while many of these present formally defined interfaces, especially the theorem provers, the implementations are almost never actually written to be formalized. So, well, how much are we actually talking about proving here? Well, one way you can think about it is, you know, software correctness is a property not of physical computers. It's relative to the abstract model that is provided by the hardware. So software correctness is a mathematical statement. Mathematical theorems can be proven, so we can eliminate all software bugs. So what's stopping us? I think that at this, you know, point in our development as a community, we have solved problems at this level already. We've solved very large mathematical theorems. We've proven large algorithms correct. And the algorithm that is a theorem prover is not that complicated if you do it right. So this is where this new language, Metamath Zero, that I'm designing comes from. So this is designed sort of from the ground up as an efficient back-end theorem prover. So I want to emphasize that the focus here is sort of not on the user interface, but rather on being sort of an assembly language for proofs and just doing really well at the back-end part. Because I think that there are a lot of theorem provers that do very well at getting the user interface right, but when it comes to the back-end, they're just slow. So Metamath Zero is surprisingly fast. It's slightly faster than Metamath, which is based on a very simple sort of string rewriting. It's basically repeated string rewriting, and you can verify mathematical theorems that way. And when you design a verifier like that, you can just blaze through these proofs. So this thing can run at about 100 megabytes per second of proof data. So that means that, you know, it can verify this library of 30,000 proofs. The prime number theorem is among those proofs in half a second. And the material for this project, I wrote a small library of facts about P&O arithmetic, including things about, you know, lists and vectors and bit vectors, and we'll get to that. But the entire library for that checks in 5 milliseconds. So this is something, you know, you can almost imagine maybe running this at boot as part of your trusted computing base, but we'll leave that till later. So the actual verifier here, the C verifier is written, it's about 730 lines of C, and that goes up to about 1,500 lines of assembly. And the plan is essentially to verify this at the x86 level. So there's some additional tooling which is written in Haskell for doing some proof authoring for this. It's got VS Code integration and so on, and I'll show some of that in the demo. And it also, as a backend theorem prover, it emphasizes translations to and from other languages. So some theorem provers are better than others as far as being able to take the data that you have inside your theorem ecosystem and moving it to another theorem prover. And I think that that's very important. So right now, we have translations from Metamath to Metamath Zero, and from there to open theory, as well as to Lean, using translation through higher order, to a subset of higher order logic. One of the major design decisions here is that there's sort of a separation between the theorem statement and the proof. So the idea is that you have one part is the trusted part that states what is the thing that is being proven, what are the axioms that those are being proven from. For that, you only have to state the definitions that are involved in the statement of the theorem, not necessarily additional definitions and additional theorems that will be needed in that proof. And you don't provide the proof itself. And then the proof is provided in a binary file format that is very easy to read by the verifier. So why x86? So there are other instruction sets out there. RISC-V is one I've been looking at. But one of the things that I don't like about choosing a sort of alternative is that it's very easy for anyone to sort of, on their laptop or whatever, find one of these Intel x86 machines. Unfortunately, the reality is that these other hardwares are just harder to get to. So if the goal is to have, if you prove a theorem and you want to show everyone, like, no, this is really true, you really need to be able to have anyone pick up their machine and be able to check it. So the operating system is one thing which, you can think, do we really trust the operating system to treat my data well? Well, you can do it on bare metal, but again, this causes issues with being able to run it on, anyone's machine. But it doesn't make that much of a difference for this main project. So for this, I'm primarily focusing on Intel x86-64 with Linux running on top, and I only touch a very small amount of the Linux kernel. So this still leaves a lot in the trusted base here. So the idea is we want to be as certain as is reasonably possible that this thing is operating correctly to the best of our ability. So when we start getting to the edge cases, you start thinking about some unusual things. Like, for instance, I'm running my program and it has some memory, and I need to make some assumptions about the memory is not going to be tampered with while I'm executing. If that happens, then I could end up with the wrong result. But the fact is that it's not, like, if I state, a theorem based on the assumption that that memory is not going to be tampered with, that assumption is not true. There are actually a variety of ways that different different software running on the machine simultaneously can muck with your memory. So, a debugger can go into your memory and change whatever it likes. Similarly with root privileged software, and then going even lower, the firmware and the hardware have the same abilities.
How about you're executing a secure enclave?
Say that again?
You're executing a secure enclave, and you don't trust the OS.
Right. So one hope is, I mean, if you're running on x86, it's not clear how much of the firmware and so on that you can make sure that this isn't going to happen. But at the very least, you probably want to cut off the network connections and make sure that these sort of backdoors don't happen. Oh jeez. And of course, large parts of the firmware can't even be checked for their correctness because they are opaque binaries. The Cartesian daemon is a problem by René Descartes about whether a daemon is modifying my perceptions of the world. And there's sort of an analog of this in computers where you ask, okay, fine, I've got this verified program and it's going to run and it's going to give me the right output, but how do I even know that the program ran when I told it to run? Or how do I know that the thing that I typed is the thing that ended up in the program? And how do I know that the program, when it returns a value, is actually displaying it? This is actually a concrete problem that comes up. Like, if you've used some theorem provers, you might have had the experience that maybe it's trying to report an error, but it actually crashes, and it doesn't report the error. It just shows nothing, and you think because it shows nothing, oh, everything must be fine, and my theorem is proven. But actually, no, it's crashing. This I think is a concern, and the ability to verify things about this is actually very difficult because actually, the operating system and the firmware and the hardware all touch that input-output pipeline. So moving on. So for the actual formalization of x86, I actually looked around and I noticed that there were actually several formalizations, several of which are actually here today. And so I mainly considered these two. I hadn't heard of the Isabel project, but it's very good to hear that they are working on sort of cleaning up that strata output. That was a big problem for me when I looked at the sale. The fact that we have thousands of files and they're all these sort of unreadable messes is very difficult for sort of human usage because I'm attempting to actually work with this, and somehow that's an issue. Yeah, I looked at the sale version, and the sale people had this formalization. It's like, oh, it's this little throwaway thing. It's probably wrong, and it's only half of it. And it's like, well, that's perfect. I actually only need a few instructions in order to verify proper. In order to verify a verifier, if you already know what the program is going to be, if it's the same program, then you can actually just keep it to a reasonable subset. There were a few minor bugs in it, but nothing major. I was mostly comparing it against the Intel documentation. So I did actually have to hand translate these. Yeah, translations and cross-validation are very important for this sort of thing. Maybe I'm not as naive as I thought I was when I wrote these slides because of this morning's talk. So it's possible that Intel will actually be able to give some proper guidance on this. Okay, so let me actually show you what this sort of looks like. This is what the let's see, make this a bit bigger. Close this. So this is what the language actually looks like, and I would say it's roughly average for these sorts of theorem prover languages, but the fact that it's being parsed in very few lines of code is important. So this is sort of an attempt at being a trade-off between human readability and ease of parsing. So like these $ signs here are to delimit the sections that the dynamic parser is running, and then the static parsing is being done outside. So you can declare some infix notations and so on. You write down these theorems about the definitions that you make. You can declare, in particular, you can declare, and I'll talk about this on the slides, you can write down a definition, you don't say what the definition is. What this is saying is, well, there is a way to define this thing as some concrete term for which these theorems hold. Right? So, so this here is actually just defining Peano arithmetic. You know, you write down a few axioms, and then you're in business. You can define numbers. You write down, these are the actual axioms of Peano arithmetic. The earlier ones were first order logic. And defining pairs, first, second, power set.
Is this sorted first order logic?
This
Underlying logic here, or?
So the MM0 itself has a pluggable axioms set up, so that's why this thing starts with you get to define implication and negation, and then you start working with those objects. So it's somewhat like Isabelle Pure in that regard. So in 300 lines we can define all of the basic definitions we need for Peano arithmetic, and then we get to x86 itself, which after a few more definitions for bit vectors, we just start writing down, what are the registers, how do you read a displacement, how do you read the SIB byte, and all of that. This here is how do you read the mod RM byte, and it's just a term of first order logic, essentially. Oh, and this is currently running in the with the server, so if I make a modification here, it's actually checking live. So if we go down here, so this is how the decoding works, and this is the dynamic semantics. And then the core of it is a step relation. So you have some state of configurations, and then you declare that you read what's at the instruction pointer, you decode what's at that instruction pointer, and then you execute the AST that was corresponds to. Okay, so remarking on a few interesting points about this, I guess, for inductive types, so this thing does not know anything about inductive types, but for computer science applications, it's very important that we have something that acts essentially like an inductive type. But one thing that you can do is you use this sort of idea of the abstract definition, and then you just sort of write characteristic equations for that. And you end up with a style that looks roughly analogous to, I think, the way you write down definitions in Isabelle, where you just say, here's a bunch of equations, and then it solves it for you. Here, we're not solving it, we're rather asserting that this exists, and then the proof authoring part is responsible for the actual solving of these equations. So the nice thing about this is that you don't have to just write down concrete definitional terms, because those will probably be less clear, and it's also very flexible with respect to different shapes of induction, in the sense of you might want to define something by induction on lists, but you want to do it on lists from one end and then lists from the other end. And this is something that in a dependent type theory like Lean, that would actually be pretty difficult to do. But it does mean that the reader, so these are all part of the trusted part, right? This is stating what ought to be true of these functions, and the reader actually has to know that these are complete. You can assert that these are complete as an additional theorem, but then it starts to get unclear whether you've even won over the original approach of just writing down a definitional term where you say, oh, this is the induction operator applied to some stuff. And also, if the equations are non-exhaustive, then the definition is allowed to resolve in any way that the prover would like it to be. So it's sort of resolving in the wrong way. You'd like it to be like some sort of axiomatic thing, but here it's actually the opposite, where the prover actually gets to decide, and maybe they're deciding sort of in their favor, and you want this to have as strong as possible.
Can the equations be self-contradictory?
So if the theorems are contradictory, then it will not be possible to prove the theorems. So you will not be able to provide a proof term that is going to actually check through all of these theorems. So an essential part of this is not only you have the specification of the theorem, but then someone also gives you this proof that will then run through the verifier and ensure that all of these are actually correct. For typing, it's just encoded in logic. I don't think I'm going to say much about this. And so, yeah, the high-level semantics is that there's a configuration which consists of the instruction pointer, a bunch of registers, the flags, and the memory. And then this step relation will terminate when it's invalid or when it's an uninteresting opcode. But it also terminates at syscalls. And then in order to handle syscalls, we extend the state with some pseudo-fictional input and output streams. And we say that if you read from input, it pulls from that input stream. And when you write to standard out, it writes to the output stream. So we have a basic implementation of the ELF file format. And so we end up with an end-to-end semantics function where we can say, here's a sequence of bytes which have come from an ELF binary, and then you end up with a non-deterministic function that says, given an input, here's this, a sequence of possible outputs, and that output is actually probably going to be like a 0 or, well actually, I think this one is just, it's going to check that it returns a 0, meaning success, and then it gives you the output. Okay, so as a summary, this is an ongoing project, and the main part of it is actually to prove those theorems that I pointed to. But right now, there is a lot that has been done to build this theorem prover that can work with this material. So thank you.
Thanks to the Cartesian daemon, we had a bit of delay, and we've had a few questions already, so perhaps just one very quick question if there's one more. Let me just ask, so you mentioned that the sale was something that you could use, although you couldn't kind of directly parse it.
Mm-hmm.
So in the end, are you essentially using it in any programmatic way, or are you just using it as inspiration for writing stuff yourself?
So it was mostly a transliteration of the sale. So the sale is this program written in this simple ML-like language, and you can just write down the clauses. So that was basically what I did, and then I had to make a few modifications. I think I dropped some instructions that weren't necessary, and then I think I added like 2 or 3 instructions, but not that much.
Okay, so let's thank our speaker again.